number 7 on page 44, and it's a different type of a time, distance, speed problem. In this problem, it states that it took a patrol boat 5 hours to travel 60 kilometers up a river against the current and 3 hours for the return trip with the current. Find the speed of the boat in still water and the speed of the current. So let's say that this is my boat and it's traveling 60 kilometers an hour, 60 kilometers for 5 hours. Now, when it comes back, it takes for the same distance, exactly the same distance, it takes the boat only 3 hours. Now, imagine the boat being in blue, and now let's take a look at the current. Now, when it's going against the current, that current is pushing against the boat. Imagine that you are trying to move forward, for example, in rugby, right? If you're trying to gain some of the field to take over the opponent's field, they are pushing onto your shoulders. They're slowing you down. The harder they push and the faster they move, the slower you will move. So this red arrow is the speed of that current, slowing the boat down. When the boat returns, the current and the speed and the boat move in the same direction. Imagine that somebody is pushing you from behind, giving you a boost. So then you're going to move faster by how much of a boost you're receiving when you're moving in the same direction. So if we label the speed of the boat B and the speed of the current C, let's see if we can find some equations to solve for the speed of the boat and the speed of the current. Now we know that our basic time, distance, speed equations is distance equals speed multiplied with time. Now what do we know? In the first scenario, I know that 60 kilometers were traveled in 5 hours, but at what kind of speed? Like, what was the speed in those 5 hours? Well, as we figured out over here, is the boat had one speed, but it got slowed down by that current. So then if the speed of the boat was slowed down by the speed of the current, then the combined speeds are less than what the boat would have in still water. And I could represent it as B, the boat, minus the speed of the current. In that second equation, I have the same distance, 60 kilometers equals. Now, this distance was completed in only 3 hours. And let's take a look again at those speeds. Well, it's only 3 hours because the current gave the boat a boost and made it move faster back to its origin point. So then to the speed of the boat, I'm adding the speed of the current. Well, now I have two equations forming a system, and all I have to do is make sure that I can expand this side of each equation. So let's see how we do that. We have 60 equals 5b minus 5c. And over here I have 60 equals 3b plus 3c. Well, since the c's have opposite signs, which means that I would only have to add the two equations to get rid of the c's, I'm going to choose to bring these ones to the same common coefficient. So I'm going to multiply the first equation by 3 and the second equation by 5. And what I get is 180 equals 15b minus 15c. And times 5, 300 equals 15 B plus 15C. Now I can add the two equations together, and the C's are eliminated, and I'll have 480 equals 30B. I can divide both sides by 30, and B will equal 16 kilometers per hour. Now that I have the speed of the boat, I can find out the speed of the current, which is 60 equals 3 times 16 plus 3C. So I'm going to move the 48 over, and it becomes 12 equals 3C. Divide both sides by 3, and then the speed of the current is 4 kilometers per hour. As I mentioned, it's just a different type of time, distance, speed problem that I highly encourage you to practice, as you have plenty of examples in your textbook, such as example number 13 on page 45, or small twist on the same problem, example number 17 on page 45.